Hi, my name is Henk. This is the first part of a set of videos. The first part is about the hardware of a music box that can play any MP3 file of your liking. So this is what we are going to create, and I will explain in detail how it works, especially the low power part. If you want to create an Arduino based application and it should be low power, then this video might also be interesting for you. Hello, my name is Henk. If you like this video, then please subscribe to this channel. That will help me in creating more of these videos. So what's the plan? Today we want to create an MP3 player. So you see a picture on the screen. And actually that's something which you can buy in the market, but we want to create it ourselves. It should be battery operated. And you should be able to put any MP3 file in it, so you can adapt it completely to your liking. So what we will do is create the hardware as well as the software, and we will do a casing, and the casing will be a laser cut design, but you can do it also yourself. So first we'll focus on the hardware of I've decided to do it Arduino based, so there are a lot of low-cost modules which you can choose from, and one choice is, do we use an Arduino Nano or a Pololu A-Star board? Well, the Pololu A-Star has a benefit. It is smaller in size and it has a separate UART, but we're not even going to use that separate UART. But most of my things which are small, I use that board, so I selected it to use for this application also. Then there is an MP3 module with data storage on it, so that's very important because we should keep those MP3 files somewhere. So there's an SD slot on this MP3 player. On the market you will find it as a YX5300 board, but it actually contains a different chip. So you should always check which chip is on that board, because it has a little bit different commands. We'll come back to that in the software. It's controllable via UART interface, so an RX and a TX interface, receive and transmit serial data, and it has a supply which is between 3 and 5 volts roughly. Then we need a Class D amplifier, actually a mono amplifier. We're going to use only one channel out of that serial interface. That's the PAM8302 module. It is a 2.5 watt amplifier, so that's more than enough for this application. Also with a supply range up to 5.5 volt. Then we need a peer sensor, and that should be low power because it is always on. The standby current is 20 microamps, so that's low enough. Supply is between 3.3 volt and 15 volt, so that's also okay. So that's the ASR602 which I selected for this functionality. And the special part is of course the power circuit, because that needs special attention due to our low power requirements. It should be battery operated. Well, the CPU and the pair should be always powered, because that's our basic functionality to detect if someone is entering a room or is present in front of this thingy, and then it should start playing music or whatever you put in those MP3 files. The CPU in sleep mode consumes roughly 200 microamp, but that's the CPU alone. That's not the whole A-Star board. The peer sensor consumes 20 microamps, so that adds up to 250 roughly. So what if we would calculate it based on 300 microamps? Then we would have a 290 days usage, so that's good enough. If this was 14 days, then it's of course not good enough, but this is okay. This means we switch the power completely off, and we also want to measure what happens in sleep mode, because you can put the MP3 player in sleep mode and you can shut down the amplifier. there's a shutdown pin. And we just want to measure that to be sure if it was a good idea to completely turn off the power and invest in additional hardware for that. So what would our design look like? Well, we currently have a system which should have 4 AA batteries. So that means the power supply is between 4.8 volt and 6 volt, dependent on which batteries you are using. We should take into account that people could put in 1.5 volt batteries in there. And that will be connected to the VBAT input of the A star module. So the output of the A star, because it contains a 3.3 volt regulator. And that will be powering the PIR sensor. And then we also need a supply for the MP3 player and the amplifier, and that should be flexible. And therefore we need a controller, because the 6 volt is too high for these modules. At least for the MP3 player it is too high. And therefore the power supply should take that into account, and we want to turn it off. And to turn it off, we put a P-channel MOSFET in front of the supply, and that could be controlled via an I/O port of the CPU. And I'll come back to that on the next slide, why there is a transistor in between. That's shown over here. So the MOSFET, I used 2 types. The A0301A, that's the one which I finally used, but the other one will also work. These are available everywhere. And make sure that the source of that MOSFET is connected to the battery. That has to do with the diode, which you can see in the drawing. Otherwise the diode will conduct and your system won't work. So I added a 10K resistor to put the gate high. And that's actually when the power is off on the drain, so then the drain is 0 volt. When you put the gate too low, and that's in this case done by the transistor, then the power is on. And how do you make the transistor conduct? Well, that's by putting a 1 on the on-off input pin. So a logic 1 will result in a conducting transistor, and that will pull the gate low, and that will turn on the power. So this transistor also inverts more or less the logic, and we cannot connect the I/O port of the CPU directly to that gate, because the gate will be 6 volt. So that's not a good idea, because then we have a too high voltage on the CPU. We need to create for instance, a 3.3 output voltage. And that's done by a 317 device, and there you can calculate what the resistors should be. So there is a formula in the datasheet which is shown over here. The I adjust multiplied by R2, so that's the current for adjustment. That can be neglected, that's microamps, and the other thing is in milliamps. So that means also you cannot make the resistors R1 and R2 too high, because then you get into the microamp range of the control system, and that would mean it doesn't work anymore. So therefore this circuitry will always consume a couple of milliamps, and for low power designs that's not good. So therefore the MOSFET is in front of the 317 and not behind the 317, because otherwise there would always flow current through R1 and R2 of milliamps. I choose 470 ohm for the R1 resistor, and then you can calculate that the other resistor should be in the range of 470 ohm plus a 470 ohm or 1K ohm potmeter, to have a range between 2.5 volt and 3.75 volt or 5.16 volts, so that's okay. So whatever you choose for the potmeter, that's up to you, both will work. The total circuit will look like this. So you have a battery which is powering the circuit which we just discussed, and it powers directly the VBAT of the A-star CPU. The 3.3 volt VCC of the CPU will power the peer sensor, and the output of the peer sensor is connected to an input port of the A-star CPU system. An output which is pin 3 or port 3 will turn on and off the power. Then the 317 will power the MP3 player and the amplifier, and the pin 4 of the A-star, which will be the transmit, will be connected to the receive of the MP3 player. So some people think that RX should be connected to RX. Well, that's not the case. In UARTs it's always a crossing. The transmit signal is connected to the receive pin and vice versa. The receive pin of the CPU is connected to the transmit pin of the MP3 player. Then we use one channel, so I chose the left channel that's connected to the A plus of the amplifier. The A min of the amplifier is connected to the ground pin of the jack plug of the MP3 player, and then you connect a speaker, and that's basically it related to the hardware. And the hardware looks something like this if you would build it on a board. So over here we have the 2.2 ohm resistor, which is in series with the battery to measure the current by measuring the voltage over these two wires over the resistor. Then we have the power circuitry over here. The MOSFET is actually a very small tiny thingy which is at the bottom, located there. And this is the MP3 player with the SD card in it, and there you have the amplifier and the CPU system, and that's actually everything which there is. But we also have, of course, the peer sensor connected with a small cable. So that's the hardware. And going back to the slides, or to the discussion, I measured the current. So in power on and the CPU in sleep mode, we have a consumption of roughly 23 milliamps. That's shown on the right diagram, that we measure the voltage over the resistor, and then by Ohm's law you can calculate the current. That's pretty simple. The power on and sleep mode for the CPU, and we put the MP3 player with a command in sleep mode and the amplifier with the shutdown pin in shutdown, then we see that the current consumption drops to only 20 milliamp, and that's way too high for a sleep mode. So actually it is a good idea to have that MOSFET in front of it to completely turn off the power, because these sleep modes are not good enough for low battery operation. Then in power on, when music is playing, we see a consumption of 33 milliamp, and that could be a little bit higher if you turn the volume up. The power off and sleep mode, so that's the case where we actually use that MOSFET to turn off the power completely. Then we see that the current is dropping to the range of 300 microamps, and that would lead to a longer battery life. So that's of course good. So over in the 3 bullets below you find that what I already mentioned, that MOSFET is required, because otherwise you have a 4.5 day, 4.5 days of sleep mode based on the 20 milliamp current consumption when we put the system in shutdown. That shutdown mode is not good enough. Switching the power off completely, so that's mode 4, then we have 9 months of operation, and that's good enough. And what would be a realistic usage and how long does the battery last? Well, if we use 2100 milliamp hour batteries and active current is 34 milliamp, then it would last for 61 days 61 hours active usage. And assume that this thing is 30 minutes per day active, then that would mean we have roughly 4 months of operating time. So realistically, between 3 and 4 months, the battery needs to be replaced, and I find that good enough for this application. We've come to the end of this video. If you like this video, then please subscribe to my channel, and thanks for watching. Goodbye.